Right. Hi, folks. As Eva mentioned, I'm Andrea. I did my PhD at ADTs in systems and formal verification, and I defended, although I haven't handed in my final dissertation copies yet, so I'm not quite a doctor formally, and I started at VMware Research a couple of months ago. So, yeah, as Eva said, feel free to interrupt at any time. The talk is very much designed to be interactive. There's a bunch of demos, which I hopefully am gonna work out. And if you're like curious about something, anything, just stop me and we can take a look. Cool. So I'm talking about Verus, which is the project we've been working on for the last couple of years. There's a lot of names on the slide, and that's because this is an effort from many people. And some of the things, or many of the things I'll be talking about tonight, are work by many of these fine folks. And we've had some also nice folks that have helped contribute via GitHub. Cool. So let me make sure that I all set up. Excellent. All right. So let me give you some context of this project and kind of how it started. I've been part of this collaboration with folks you've seen the previous slide on trying to figure out how we can scale SMT-based verification to build system software. And if you're not familiar with what SMT means, we'll get to that in a second, but this is kind of deductive, semi-automated verification. And some of our goals were to be able to use verification in the development process rather than what some folks have done in the past, which is build an artifact and then verify it. And also be able to have a tool that allows us to make the verified artifact maintainable. So we build the artifact, the proofs, and then we evolve both. And this is both about the tool, but also about the methodology that one employs to work on this larger project. So we started out a few years back with Daphne, which is a integrated verification tool, originally from Microsoft Research. And Daphne is an imperative language. It's garbage collected. It's akin to C# in many ways. It has integrated SMT-based verification, so semi-automated verification, and uses a technique called dynamic frames to reason about memory and memory using. And we'll get to that as well. So we wrote a fairly sizable project, Very Better KV. It's published at OSDI 20, where we figured out some of the methodology changes that we had to make to be able to scale up verification and full functional verification to such a larger project. And Very Better KV was a formally verified crash-safe key value store. So Daphne worked out very well for us, but we did encounter some challenges when trying to scale up the projects when using Daphne. And to address that, we built Linear Daphne, which is an extension to Daphne that introduces a linear type system for Daphne. And we published this at UPSLA last year. And this is coming also with some deterministic memory management. So here we're kind of taking Daphne, and if you're familiar with what a linear type system is, we're trying to make it closer to Rust in some ways. We're going to try to have the same ownership semantics. We'll get to exactly why again later. So having done these two things, we kind of took a look at what languages you might want to use for system software verification. And if you think about the languages you can pick, there is some languages that are more close to math, like to regular mathematics, where maybe you write mathematical code and then you get extraction to get the actual executable code. And on the other side is languages that are closer to computers, so actual imperative code. And a lot of system programmers do prefer writing software in languages closer to the computers because they have more control of how a program executes, the memory management, and the algorithm they're running, and all of the phenomena that you need to be worried about when you're writing high-performance systems code. So on this spectrum, Rust is an interesting point because in many ways, Rust is efficient and predictable, like C, like a language very close to computers. It's imperative, no GC, implies mutation, zero-cost abstractions, all things you probably know and love, and low-level operations like unsafe. But at the same time, Rust, safe Rust at least, is pretty much close to being a functional programming language. And if you're not convinced yet, and you might be because you've seen some of the talks from this working group before, we're just trying to convince you that safe Rust is in fact very much a functional programming language. And it also has a bunch of features that are very convenient when you're writing complex logical statements and proofs to write your fully verified software. So algebraic data types, pattern matching, restricted set effects. All right, so because of this, we have been building Verus. Verus is an SMT-based intrinsic verification tool for safe Rust code. And there's some caveats here that I'll get to. We focus, and we will see if the focus is on safe Rust, but we do have some techniques that we'll look at later to handle paradigms that require unsafe in regular Rust, but do not strictly require unsafe in Verus. But let's start with intrinsic verification. What does that mean? That means that each function has a for logic specification. And here is where we are starting to hope that the demos are going to work. So this is a very simple Verus function. There is some noise at the top that we're working on removing. And then there's this, which we're going to ignore for the moment. So we have this max function that has a specification, as we were saying. We're writing a for logic specification on the function that says the result that we get from the max function is either A or B, and it's greater than both. So this is a reasonable, hopefully, specification for max. And if we run Verus on this program, Verus tells us that the post condition is not satisfied. And it tries to be helpful in pointing out exactly where the problem is. So you may have guessed where the problem is here. I have intentionally swapped A and B. And so we were actually returning the minimum. So if we then rerun Verus again, we get a successful verification. Now pause for a second just to make sure that nobody has questions. Excellent. Again, feel free to stop me at any time. All right, so that's intrinsic verification. SMT-based, what does that mean? And I know some of you are probably familiar, but I'm going to just kind of quickly go over this for those who aren't. So SAT is the term for Boolean satisfiability problem. There are SAT solvers that try to find an assignment to variables to a Boolean formula such that it's true. So you can have formulas like these. You give them to a SAT solver. Maybe Z3 is a bit excessive as a SAT solver, but it does a fine job at being a SAT solver too. And it will find these assignments that if you go and substitute the variables in there, satisfies that formula. There's an extension to SAT, which is SMT, satisfiability module theories, which essentially generalizes SAT to more complex formulas. So tools like Z3 allow you to write expressions that contain real numbers, integers, various data structures, and quantifiers like for all and exists, which are helpful to express how a program should behave, and then also to express what the semantics of the program are. So we can, for example, ask it whether for all A and B, we can give it some expression like this: for all A and B, A times B equals B times A, and it will tell us if that's the case or not. So let's look at how we get to SMT-based verification when we try to build a verifier. So here we have the max function from before, and then there's this kind of traditional way you would test this. I just pick two values and give it to the max function, and then assert the properties that we intend for the returning value. So this is testing a single point in the space. And I'm going to be quickly here because I imagine a lot of you are kind of sold on the idea of instead of doing one point test, we're going to try and do this for all A's and B's and trying to have a formal proof that this is the case in general. So how do we use a SAT solver or an SMT solver for this? So we want to prove that for A and B, our specification is true for that function. Now we can rewrite that expression to be there does not exist an assignment to variables A and B such that it's not the case that our specification is true. And now if we do this and we just stake that part that exists, this is exactly what SMT solvers are designed to look at. And in fact, an SMT solver like Z3 will tell us that there does exist such an assignment, which means that in fact we couldn't verify what we were intending to. So that's what might have happened before when we couldn't verify the program from before. But if Z3 tells us unsat, it means that there does not exist any satisfiable assignment of these variables to this expression, meaning that we've now found the proof. We were looking for does not exist, and now that means that for all A and B, this is true. However, very often, at least depending on how you approach this, and I'm not going to go into a lot of detail here. There's a very broad set of concepts to explore, but there's many situations in which SMT solvers have to be incomplete or just take a long time to determine to find an answer, because they have to rely on heuristics to go and find this unsat result. And so it's very important, if you're trying to scale up these verification projects, to find a way to be using these tools in an efficient manner, where we minimize the cases in which the solver just spins out of control or tells us, well, I'm not sure which way is which. So this is why one of the first focus of Verus is efficient SMT encoding. We've learned some things by using Daphne. Like Daphne works pretty well in some circumstances, but produces fairly large encodings, and encodings that have a bit of a bigger tendency of causing SMT to spin, Z3 to spin. We are focusing very much on having an encoding that's efficient and will be solved efficiently by the solver. Verus has harder features though, because again, the goal is to build a verifier for large-scale system software and high-performance system software. So there are circumstances in which we may want to not use the regular Z3, but some other solver, because that's more useful for a specific problem. We'll take a look at one of those. And then we use linear ghost types for proofs and concurrency. And this is a topic that, again, I'm going to cover later. And something that I'm not going to have time to cover is there's also state machine syntax that's TLA plus inspired, if you're familiar, which allows you to write specifications of complex concurrent software. Asynchronous software, I suppose. Distributed programs, for example. So there's another caveat that I had on this line, which is that Verus is a verifier for a dialect of Rus. Let's look at what that means. So as you may have noticed before, there is some part of the syntax here that it doesn't look like kind of regular valid Rust syntax. And this is because we've been working on a syntax extension to Verus to Rust using a macro. And I think Chris Hoblitz at MSR is in the room and has done a lot of the work on this. So to provide a language that is intended for, it's in some ways similar to the things we liked in Daphne. It allows you to naturally provide, for example, function specification like this, and has features that are useful when you're using the Rust language to verify software. So in that sense, it's a dialect. It's mostly Rust. Most Rust expressions are valid Verus expressions, at least the ones that are supported. But there are additional concepts that we have added on top to make the specification and verification more natural in the language. Cool. So let's look at how you might verify an actual function in Verus. So here we have Fibo impl, which is an implementation of Fibonacci, the kind of not entirely naive version. And obviously, if we ask Verus about this, we have actually a couple of missing function definitions. So we are saying that the result should be Fibo of n, but we haven't actually said what Fibo of n is. So we're going to go and grab a file that does have those definitions. So here, Fibo is a spec function, meaning a mathematical function. We'll be more precise about that in a second. And here, this is the mathematical definition of Fibo that you're almost certainly familiar with. And we also need something else, which is if we hope to produce a valid result, we need to know that the result of Fibo impl actually fits in the result. So we define this. All right. So now that we have actually defined our Fibo and Fibo fits U64 functions, we can ask whether Verus believes that this program is in fact equivalent to this mathematical function, which is what we asked it to do here. And that's we believe that's the case, but Verus does not believe us yet. And the reason for this is to start that we didn't provide any loop invariant. Verus does not attempt at the current time any loop invariant inference. So we have to provide a loop invariant here. So we're saying that within the loop, I is within the range we expect, and especially current and previous are the current Fibonacci value and the previous Fibonacci value. And building on this, we get information at the end of the loop that hopefully lets us prove our post condition. So as we said, we saw that the post condition was not satisfied. So this was over here. If we run this again on Fibo 2, now we don't get the post condition not satisfied error anymore, because our loop invariant is enough to allow Z3 to prove that post condition. But Verus is still not happy because it believes that core plus prev might overflow in this case. And also that this may not be satisfied at the end of the loop body, and that's just a side effect of not believing this expression. So our fix for this is actually to introduce another concept in Verus, which is a proof function. This is Fibo is monotonic. A proof function is the way we would write a lemma. If you're familiar with Daphne, it would be a lemma in Daphne. And it has, again, a specification. It is a recursive proof, so we have to prove that it terminates, so that it's well-founded. And this is just proving that for I less than j, Fibo of I is less than j, or Fibo j. And I'm not going to go into the details of the machinery. This is kind of controlling definition of visibility. Suffice it to say that this is how we prove this lemma. And now, once we have this, we need to potentially be able to use it. And this is how, when we introduce a proof block in the executable function, where we say that lemma Fibo is monotonic, we invoke that lemma and use that result to hopefully, finally, prove that our Fibo implementation, in fact, matches Fibo. Cool. So this is how you verify a function. Any questions about this? Excellent. Oh, yeah, we have a question. Go ahead.
I have a quick question, Andrea. I couldn't. What is the connection between Fibo is monotonic and the error that you had earlier? But this is very unimportant, so let's not derail you. Please continue. We'll come back to it later. It's a very minor issue.
Yeah,
I get the broad idea. I proof blocks and so on. It's pedantic. Let's come back to it later.
No worries. Thanks for the question. Maybe we'll get back to it later. But I believe the reason. So I had written the proof a long time ago, so I don't actually immediately remember. But I think what's going on here is we are saying that previous is less or equal to current here. And we know that the Fibo of n, actually, yeah, right, there we go. So previous is less than current due to the postcondition from the lemma. But more importantly, Fibo of I, this is the actual call to the lemma, is less than Fibo of n because we know that I is less than n. And this means that Fibo of I is now less than the U64 max. So to convince Verus that this doesn't overflow, we are convincing it that the Fibo of I, which is what we're about to compute, is in fact less than the biggest Fibo value that we are ever going to compute in this function call, because that's the end we're targeting. Does that answer your question? Excellent. Thank you. Yeah, no, it's great to take a look at these, so make sure that folks are on board. Cool. So what you saw is this function over here and our proof. And this is the perfect point for me to introduce the various modes of Verus. So we saw exec mode, which is an actual program code that we intend to execute. Inside that exec mode code, there is some proof mode code, which means that it's statements and expressions that we're using to express our proof or to express lemmas. So this is proof code. And then we have some spec code. So a spec code is what is mathematical language that we use to express pre and post conditions, assertions, invariants, any kind of mathematical expression of the program state. All right. And so in Verus, you mix these in the programs you write, and you can typically embed higher level modes, so spec mode, in proof mode and in exec mode. And you can embed proof mode in exec mode, but not vice versa. So for example, we can't have exec mode in code in spec mode because that would mean our mathematical specification actually has some executable code, which in our model does not make sense. All right, so now that we've seen this, let's come back and kind of talk about the fact that I mentioned we kind of came to Verus and came to Rust because of challenges that we encountered in Daphne and in memory reasoning of these larger scale systems projects. And as I mentioned, we built this linear type system for Daphne, and let me kind of give you the motivation for why we embarked in this some time ago. So this is Daphne, it's a different language. This is hopefully the syntax is familiar enough. And what we're trying to say here is that we have an account, and this is in Daphne, it's a reference type. This is going to be allocated on the heap, and we're going to keep a reference to it, which is a little different from Rust model. It's more akin to C#. And we have a method transfer that transfers some funds from the origin to the destination account. We're saying that the balance in the origin is greater than the amount. And because we need to be able to do that to transfer the funds. And then we're saying, well, at the end, we've transferred the funds according to the specification. And all here means the state of origin and destination before we run the function, at the start of the function execution, and then these without the old in front of them is the final state. So you can see here, I'm doing something sneaky, which is calling transfer with the same account. And you might realize here that if we did this, the specification of this function would actually not be true. And this is in fact caught by Daphne that says the post condition here might not hold. However, interestingly, is like this is a fairly simple program, and I've already given you kind of a hint here. But if you didn't have the main method and you were just staring at the transfer function and trying to figure out what's wrong, you will be surprised to hear this. This is a very trivial program, and the only thing that's missing, and then Daphne requires for this function to verify, is an explicit statement that origin and destination are not aliased. So if we add that line, then the transfer method finally verifies, but we now get an error here that says a precondition to this call might not hold because we are aliasing account here. The problem here is when we got this error, we didn't really know, is this like a real logic error? Like did we do the math wrong somehow? Or did we miss what's called a framing condition? So did we miss the requires that says that the two parameters are aliased? And this is kind of in a nutshell, and this kind of compounds when you scale up the complexity because of the specifications, for example. But this is in a nutshell the issue that we encountered with this style of memory reasoning. And so the idea here is, well, instead of doing that, let's try and rely on the Rust linear type system instead. And obviously, especially if you've been to this these meetups before, you know that we are not the only ones to have these ideas in some form, but this is kind of the way we got there. And so let me show you what the same program looks like in Verus. And here, this is kind of a talk that I've taken different shapes for different audiences, and I know that you folks are probably kind of very familiar with Rust, so I'm not going to belabor the point of ownership here. What's interesting here is in contrast with the Daphne program, we know that origin and destination couldn't possibly be aliased because we have a mutable reference to each. And so, as you know, these have to be exclusive. And so we have to specify no framing invariance, no framing requires, and we get this to verify. And if we now, attempted to do what we did wrong before, and call this function with an aliased account, now it isn't the solver like it was in Daphne, but it is the Rust type checker and borrow checker that are catching this mistake. And so let's actually fix the program. Xavier, go ahead.
I have a quick question.
Yep.
I noticed you have old in your specifications, especially in the requires, which is a little bit unusual.
What
are the semantics of old in preconditions?
Old is required in a precondition as it is with the current syntax, if you're referring to any variable, essentially. So there's kind of two syntactical choices here, which is either you say, we're interpreting these expressions in the context of the start of the call of the function, and then you wouldn't need an old. Or this is the approach where we are saying, well, we're going to use the same interpretation. Old is at the start of the function, and the regular name is at the end of the function call. And now you have to actually say old. And in fact, I think if I don't here, Verus is just going to tell me that you have to use old to refer to the pre-state of a mutable variable.
Okay. And one other minor question: what happens if like org is itself mutable, like a mutable binding rather than a mutable borrow?
A mutable bar. You mean mute of origin? Is that the question? Just okay. Right. So I think what we do right now is that we just don't allow you to do it. And I am not going to try and figure out where the problem comes when we do that, when we allow you to do this right now. But great question. So this is, I guess, a great time to mention that Verus did not prioritize supporting all of Rust, not even all of safe Rust. Our priorities was building the language and the tooling that we thought was useful to build this larger system software. And we had learned that you could build fine system software with linear Daphne, which was a much more limited type system even. Like it doesn't really have the mutable borrows or kind of the non-lexical borrows that you have in Rust. And you can still write fine software with it. It's less convenient, but researchers are happy to put up with more pain, I suppose, when writing software. And this doesn't mean, obviously, that we're not planning to extend our support, but we focused on getting the tooling right, getting the encoding right, getting the experience right, and then we are kind of extending support. Possibly the goal never really being maybe supporting the entirety of safe Rust. We might get there at some point, but it is not currently a priority, which I think is different from some of the other tools that are out there for Rust verification, like Xavier's Crusoe. Okay, so this is an actually correct program, hopefully. And here you can see actually a couple of assertions where we have transferred funds, and we got that result. And let's see, right. So one more thing that I'm going to use this example to show you is the fact that while these regular variables in exec code, so by the way, there's a kind of an implicit exec here. So this is any function that's not marked specifically are executable functions that we intend to actually run as part of the program. And these are treated as regular Rust variables, and so they're borrow checked. However, as we mentioned before, it's useful to interleave some ghost code, so some mathematical concepts and some ghost variables, so variables that we're using for verification but not actually intending to compile inside of exec code. And the way you do this in Verus, and if you've seen previous Verus iterations, this has changed, is by using Ghost, and actually come back to how that may work in the future. And we have this Ghost typewriter that we intend to erase from the final binary. And what's interesting here is while origin and destination in regular Rust shouldn't be possible to move out of them, you are allowed to do so for Ghost code, for spec mode code. And that's because we are just referencing to their kind of abstract value here, and we're not actually moving any memory around. And we can use this feature to then make, for example, an assertion here that says that the total balance at the end matches the balance at the start. All right. So as I was talking about, Verus trusts the Rust linearity check, or as you probably know it, the borrower. It treats data types as immutable, and this is similar to linear Daphne, Crusoe, and Nies. And in this, it's different from Prousty that re-encodes what it has learned from the borrow checker in separation logic, and then uses that for verification. So we just, like these other tools, we treat the Rust code as essentially functional code. And so the code on the left is treated as if it was equivalent to the code on the right, where each mutating operation is actually kind of under the hood, interpreted as to be something that creates a new value. And what does the at mean? Excellent question. I tried to sneak it past you. So at is view, so it's the abstract representation of that type, and it's the model, and it has, I believe, the same meaning as a very similar meaning to Crusoe, with the exception that it's postfix instead of prefix. And Xavier will correct me if I'm wrong here. Right now, I think we took a look at some of your programs, and maybe you inspired us to decide to use that as a postfix. And in part is also because it's directly translated to .view on that variable, and so it was also convenient and also easier for the user to interpret. So here, the view for these vectors are sequences, mathematical sequences for which we can reason about in spec code. Yeah, I think I've gone over everything in this lab. Very good. I'm just trying to think about whether I was missing something from the diversion. And what I want to highlight here is it's the type system that handles memory reasoning here, not the solver. So in Daphne before, I showed you this problem of like the user not being able to tell whether the error that we're getting was about reasoning about memorializing or logical correctness, where that is in part of a problem, and a problem that we solve this way, but also because the solver does not have to think about memory reasoning with kind of SMT and logic. Now we are removing that complexity from what the solver has to think about, and this hopefully gives us better performance. And if you've used Daphne in larger projects, you will maybe have experienced that as soon as your program grows a bit, the dynamic frames reasoning in the solver gets extremely expensive. So again, this is again about efficient SMT encoding, and the SMT heuristics the solver uses can go exponential with the size of the input. So our encoding of the Rust program into SMT can go exponential with the size of the input. They don't have to, but it's a kind of a good ballpark estimation. And what we do instead is we prioritize direct efficient encoding. So spec mode code, so mathematical code, is designed to map directly to Z3 logic. And spec mode, and to be able to do this, spec mode functions have to be total, so they cannot have pre and post conditions. And if you've used one of these languages before, you may think, well, that seems unnecessarily, that seems potentially annoying. Like, let's say we're writing a function like divide that divides x and y. It's a very contrived example for the sake of this explanation. Well, we know that like this only makes sense if y is different from 0, and yet it's actually a little bit of a spoiler of what's coming, which is that we are saying that, well, the function doesn't have a precondition, so we're not going to check that. Yeah, okay. We're not going to check that. In fact, let me actually show you this without this proof that fails, because it's important for the point I'm trying to make, which is if we verify this function, we are not actually going to ever, until we have a proof failure or until we ask explicitly Verus to check recommends. Recommends are ignored and they're not part of the encoding, and which again allows us to remain efficient. But now if you ever write a function like div is smaller and you forget to add the requires that y should be different from 0, now every function that's been mentioned in this proof function, we're going to try and check that the recommends for these spec functions have been satisfied. So this is a help to the user while they're writing their specification functions, but they do not come with an SMT encoding complexity cost once you've built your proof and your proofs are passing. So now we have been told that the recommendation is not met, and this is not actually a proof failure per se, it's just a hint. And it's telling us, well, you probably forgot something here, and what we forgot is that y is different from 0. So if we run this again, well, that recommendation is gone. So this now is an actual expression that makes sense, but we're still failing to verify this. And the reason for this is that by default, we do not enable Z3's nonlinear arithmetic solver, because we found it, even the new version, which is much improved, to be occasionally flaky, sometimes makes a query is not return. And it's kind of in general, difficult problem. Right. So yeah, exactly. Omitting the recommends is not actually unsound. Thanks to Lydia for clarifying. That's exactly right. What I want to show you here is the fact that we can say something like, well, not that's not the right one. Nonlinear array, telling Verus that for this function, in fact, we want to invoke the solver with nonlinear arithmetic enabled. And this is, again, we're getting back to a slide we had a little bit ago about solvers tailored to the systems problem that we're going to encounter. So this is one example of that, but another example, so yeah, this is the same we got here too, but another example of this is this other function, which is a feature that allows us to prove specific asserts in Verus, in this case, in this function, with a specific solver. So here we're going to use the regular Verus encoding and Z3 solver for most of the function, except for this assertion where we are saying, well, we want to use the bit vector solver for this. There are a couple of more solvers. I think they have them on the slide in a second. So this is because we found that applying these solvers specifically to the problems that we encounter is more effective, typically faster, and in this case actually changes the encoding in a way that would be complicated to do otherwise. So this kind of lets you keep the natural bit vector encode, like arithmetic encoding, but use the bit vector encoding for this to prove this assertion. What happens if constraints on X are not supported by the vector solver? We error generally. So some of these solvers have restrictions on what you're allowed to say. Let's I actually don't exactly remember what. And I should mention here that for some of these solvers, you have to provide the entire context for the query you're making inline. So you're going to kind of have to tell the bit vector solver what from the context above we want to bring in. And I see a question. I'll get to you in a second. I see a couple of questions, in fact.
I think Ranjit has a question as well.
Yeah. Sorry, let me finish this sentence and then I'll get to you. So let's see. Requires X different from 0. I'm actually live trying this because I do not remember what the behavior we have here. Okay, so this is supported by the bit vector solver, but we actually have a check that anything that we are using to prove this assertion is in fact true, and it isn't here. So I'm going to have to say that, or I could have added it as a request. There we go. So, Ranjit, I think you had a question, but.
Yeah, this is very neat. I like this idea of this by bit vector. I've been sort of thinking about this myself, but the question I have is, suppose in this case, I had this bit vector operation. So this mask over here, the AND, right? That you're using to, okay, you prove it over here. How do you rig it? What worries me is that what if this bit vectorness has to sort of leak out to all the clients of mod 8 BW? Bitwise, I guess, is what the BW is. You see what I'm saying? So once I put it in the precondition, in the post condition for, in this case, I don't, I guess I just have the % sign. But if I have some function whose post condition has a bit vector operation like AND in it, then probably I'd have to put this by bit vector everywhere at the call sites for that as well, right?
You don't. So you can just put in in fact, maybe we can try. It's going to take a little long, but you could totally have the ampersand here in the ensures. And while you're calling this function and you are not using the bit vector solver, that will just be essentially an uninterpreted expression. So anything that matches identically will be used for any other proof you're writing. But yes, if you are then
if you need to use the AND, you would have to put in a by bit vector at that call site.
Indeed. And so that is entirely fair point. And I guess I can share some of our reasoning here, which, it's kind of based on our experience, which is a lot of these operations, at least in using Z3 as the backend solver, are difficult to use if you let them leak out in general. Like they slow down Z3 if you try to do all of these all at the same time, and so oftentimes, even though it's a little tedious, it's better to encapsulate some of these operations. Like you essentially build an algebra that talks about the operations you're doing. There's some domain you're talking about, a page table. It's maybe like this page in the page table or this directory. And outside of the proofs that talk about the actual arithmetic, you use the algebra. And now you have to never mention the bit vector, and otherwise you do.
Yeah, I totally buy that. I've seen that same pattern in several other places. That's fantastic. Thanks.
Thank you. So Xavier, I think.
Yeah, I just had a very minor question as well about the whole bit vectorness of your integers. What's the default representation of your integers in Verus?
So you mean
a U32 normally, do you encode that towards ints, or do you encode that towards BV32 or?
Okay, I see. In Z3. So yeah, you use the default is a mathematical int in Z3 with so if it's a bounded type, like it has to be, then we emit the necessary type bounds and type restrictions.
And do you have sorry, this is perhaps a little bit too much of a low-level question, but
go for it.
I was wondering have you suffered a lot from converting to and from bit vectors? Beyond the fact that you may end up having to invoke this bit vector solver when you mention bit vector operations, but just the raw conversion cost of going from a mathematical representation to bit vector representation and back.
Suffer from like a syntactic perspective, from a user?
No, from like provability, like had the provers choke on that.
I don't think they have. We don't have extensive experience with this feature. I think the most it's been used so far, it's in this kind of page table project that we did last summer. And I think the things that we were proving there were things like bit flags, where it was kind of a natural transformation.
Okay.
And it worked out pretty well. I'm gonna refrain from making like a more general statement because I don't think we have enough data on that specific point. Yep. Thanks. Ralph's note about having to defend an Isabel person that in Coq we use specialized solvers we invoke for particular goals. So one of the philosophies that we have is at least some of us have some experience with kind of non-automated, like interactive improver kind of tools, and there are definitely benefits to those kinds of tools, and things like having specific tactics of specific solvers can be very useful to especially an experienced solver, an experienced user. So I think an important distinction here is that there's a lot of focus in Verus to try to be accessible to kind of non-verification experts. And I think we're not quite there, but a lot of the choices we're making are geared towards that direction. And if we're going that direction, then we want to introduce them to these things as late as possible, I suppose. But on the other hand, in terms of like efficiently reasoning about a complex problem, a complex system, having those features is definitely interesting. And we have been at least kind of initially looking at how kind of interactive improver style techniques could be leveraged in Verus. There's a kind of interesting issue with the paradigm of interaction of interactive improver, which is where you kind of know what your proof state is. You can see it on the screen, at least in Isabel. Whereas in Verus, in Z3, where there's a pile of facts inside Z3, and you don't know which ones are actually relevant to you. So it's a gap that's difficult to bridge, but it's definitely something that would be interesting to explore. Cool. Any other questions I missed? And then in the meantime, I'm gonna get back here to my slides. So I kind of what's the Verus binary tree roles looks like. The other scope is wrapped in a Verus macro. Looks like it was designed to be used as a macro and using cargo and RC normally to invoke. Excellent. So the Verus binary is what I'm about to say is not quite true, because going into the details is maybe a little too much, but the Verus binary is in some ways a custom driver for the compiler. So it will call the regular RASI compiler on your source code. You're going to do parsing, and it's going to do type checking. And then at that point, what we need to do is to run the Rust borrow checker on everything except spec code, even though it's not exactly what's happening right now, but that's fine. And then we want to do that first because we want the borrow checker to check that, what we did before, our mistakes that we did before in here were actually checked before we handed any of this to the actual solver. That might take longer. The borrow checker is going to be much quicker. So you've seen Verus be very quick in giving the responses right now. It's in experience been fairly quick, but the bigger the problem, the more the solver is going to take. Whereas the borrow checker will be super quick most of the time. And so we do that first, but then we steal the HIR, if you're familiar, so the internal Rust representation of the program, and use it to do the encoding in Z3, run the solver. And only then we can continue compilation and actually produce the binary. And obviously there's a way to kind of sidestep on any of these if you need to, but the sound way of building a verified binary is running the Rust compiler in a custom manner. And the reason we have the Verus macro is that we currently rely on a fork of the Rust compiler that allowed us to introduce a little bit of convenience. but we have made the decisions a few months ago for multiple reasons to move off of the fork as soon as possible. And now all of our syntax, and to be able to do so, we're more limited in the changes we can make to the language because the driver has only limited power if we're using a precompiled Rust binary to drive it. And so the Verus macro implements our custom syntax using that. Ralph.
Yes, yeah, I was, you said something about turning off the borrow checker. So now I have questions. So in the example you had here, there was about not doing a move check, like around a move, allowing a move of non-copy data. That makes perfect sense to me. But turning off the borrow checker would get a lot further, right? Like I could now have a reference to dangling data, and I could deref that in Ghost code, which is utter nonsense even in Ghost code. So, like, do you really completely turn it off? Do you have your own borrow checker to prevent this? What is the story here?
So, let me see. Okay, you said a reference to dangling data. Okay, so I think an important thing to note here is mutable. Like when you're talking about the mathematical code, you generally don't. In fact, I don't think it's even supported to ever talk about mutable references. And when we're talking about mathematical values, we treat the regular type T and a reference to T as essentially the same thing. So,
no, but your Ghost code earlier was doing star on a mute account, right?
Yes.
So now imagine that's like a box account, and then I take a mutable reference to it, and I drop it, and then I have some Ghost code that derefs it.
Yeah. So the semantics of what's happening here is we are getting, so the Ghost code, the Ghost value here is getting the current abstract value of origin and destination right then. And we are clearly assuming that these mutable references are were valid at this point, but once we are past this statement, now accounts pre remains to be the value that these mutable references had at this point in time. Am I answering the right question? I'm not sure I am.
Yeah, I mean, that makes the copy. That makes sense.
Essentially, yes. So in some ways, maybe.
But
like
the borrow checker does more than just copy protection, right? Like,
for sure.
In particular lifetimes.
Indeed. So I think the quickest way to respond to this is the spec code can only essentially make copies of values in any kind of references. It will not be able to maintain a mutable reference. And so because it can only make a copy at that point in time in the Ghost code, I don't think you can ever run into situations where your Ghost code is referencing something that doesn't exist anymore. And maybe it was too strong of a statement to say we turned off the borrow checker with the meaning you assigned to it, which is entirely fair. What we're saying here is inside of that expression, you're allowed to move out and make copies of anything, but that's confined to Ghost code. And then, very importantly, you're not allowed to do the opposite. So you're not allowed to say, here's some Ghost value, let me bring it back in one of the lower modes in proof of exec mode, because that clearly would be unsound. So once something has moved into the Ghost domain, it stays there.
Okay, I think I tried to complete my ETABS registration, and maybe I can press you with some examples in Paris.
Sounds good. Yes, so I think I'll get back to you folks in a second. Yeah, I'm happy to go a little over if you folks are fine with that. But maybe I'll come back to this question later, so I can cover a couple more things. But that's a very interesting question. Let me get to you. Yeah. Cool. So I think the quick answer is I don't think there's any way right now you can invalidate a borrow in Ghost code, but that might be something that we need to be very careful about as we add more features. So, all right, this is something I belabored, I think, a bunch, so I'm not going to talk about it too much, which is we prioritize efficient encoding. The right-hand side is the Z3 encoding of the function of checking the correctness of the function on the left. And it's hopefully clear that it's quite compact, and it's quite easy to find a correspondence here. So we're saying on the assumption that this is the return value is computed by finding the greater between A and B, we're trying to prove the two post conditions. Okay. And our experience has been with Z3 that orders of magnitude smaller queries end up having, this is very vague to be clear, but it's kind of commensurate correct improvements. And I actually think showed you a bunch of this before, which is a tailored solver for specific goals. So nonlinear arithmetic with Z3 and for modular arithmetic for kind of, we can use singular, which is a different solver. And there's folks at CMU that worked on this. Bitwise operations and proof by computation, meaning that there's an interpreter of a part of safe Rust that you can run to actually prove something by just executing it. And the last thing I want to cover is the fact that we talked about these three modes, and there's a spec mode, which we only type check and don't borrow check with the questions that have come up. Proof mode, which is type checked and borrow checked, and exec mode, which is kind of regular Rust code. But the interesting thing here is proof mode code. This is ghost code, so it's something that's not going to appear in the binary, but that has the linearity semantics assigned by the borrow checker. And by using this tool, we can write what would otherwise be unsafe code, but in a way that makes it conditionally safe. So let me first show you kind of the mechanics of this, which is how you manipulate this linear ghost objects. So these again are objects that will not appear in the binary, but still abide by the borrow checker rules. So here we have some what we call trusted functions. So I'm just going to kind of give you the definition, but we are going to ignore what they mean. And if we call linear put 0, so if we call Verus on this, that's fine. And what's happening here is saying, well, S1 is tracked. So it's a ghost variable, but we are tracking it using linearity and the borrow checker. And now if we try to exchange an S1 for an S2 by giving up the S1, and then we try to reference S1, then you wouldn't be surprised to know, if you knew with any Rust, that is something that the borrow checker is not happy with. On this, we can build, and I can't go into too much detail here in this talk, but we can build separation logic style reasoning and proofs. And I'm going to give you one example of this in a second. So this is instead of a valid use. We are going to exercise the first token by giving it an immutable reference to exercise 1, then we exchange it, and then we exercise the second token. All right, so why would you care? And the reason you might care is that you can make code that would be otherwise unsafe conditionally safe. So by that I mean PPTR is the Verus equivalent of a row pointer in Rust, where we can operate on that pointer as long as we can show we have a permission for that. And this is reminiscent of at least some of the things in Ghost Cell. But the approach here is different because this ownership is encoded as these tracked variables, and their identity, which is something that was using branded types in Ghost Cell, is tracked by the solver instead. So here is, let me show you, this is not going to be a complete example, unfortunately, due to being already over time. But the thing that's happening here is we're starting a thread. We have a pointer. This is just a regular raw pointer with our wrap around it. And we're getting a permission. So whoever constructed this pointer also got a single permission for it, and it's giving it to us, to our thread. And we're making sure that the pointer and the permission are in fact connected. There is a permission for that pointer. and the current value in the pointer is none. So what we can do is we can call send pointer and just give a copy of the pointer to somebody else. That is entirely fine. That would be potentially scary in regular Rust, because now we have a pointer, they have a pointer, we might be able to access it at the same time. But the reason this is fine in Verus is that, for example, the signature for the function put to write into the pointer, to write through the pointer, requires handing a mutable reference to the permission. And we are guaranteed to be the only one, so that the pointer is copyable, but the permission isn't. So we are guaranteed to be the only one that have the permission, and that's why we're allowed to do put. And then we can call increment, give the counter and mutable permission to that, and then we've gotten the new value. And the similar happens to borrow. And here I should point out the self for both put and borrow is an immutable reference. So anyone that has a counter and the permission can access the counter this way. So let me show you this going through, I hope. And the thing I'm going to do here now is imagine we have some other protocol outside of this. Maybe this is part of a circular buffer, and we have atomics that determine which part of the buffer are valid. Well, we may be performing some other protocol, and that protocol requires us to transfer our permission to this pointer to somebody else. So we could do this. Actually, and let me actually grab the right one, because I use the proof syntax for it. So we're saying we're going to give away the permission, and now again it's the borrow checker that's going to tell us you're not allowed to perform the increment and assert operations anymore because you handed away your permission. And Ralph, I'll get to you in 1 second. Let me just check on something, which is I wanted to mention here that these techniques that I've shown you very quickly combine with ideas that we worked on before to allow you to do concurrency reasoning with what we've been calling user-defined ghost state. So ways to represent the state of the program as a set of these linear ghost permissions, which is very reminiscent in many ways of separation logics, but it's based on Rust linear type system. And then I'll get to Ralph. I'm going to do a second ad for the Rust verification workshop at ETHAPS in April that Ralph is trying to register for right now. And Travis, who's a collaborator from CMU, who has worked on a lot of the meta theory and the implementation for this concurrency reasoning, is going to give a talk about doing that in Verus at that event. And maybe less importantly, I'm giving a talk about how to have Rust support ghost code natively, so that we can more easily maybe implement some of these tools. Ralph, what's your question?
Yes, I noticed that this tracked property is something that you have annotated at each binding, rather than it being annotated at the type, which is kind of what I would have more intuitively expected, and which is how I think the equivalent thing would look like in like the other verification tools I know about. So I was wondering if there's is there a quick answer to the why question here?
So the quick answer is we have to work with the limitations that are imposed on us by trying to do erasure using a macro. So we want to erase everything that is ghost code using a macro, but we want to be able to give enough information to Verus to then determine what is allowed. So anything that stays in kind of proof mode code and spec mode code, we've found it to be more ergonomic to use kind of these tracked variables. So with the tracked annotation, as you mentioned, but in exec code, in fact, there is the wrapper type that you mentioned. So in fact, both exist in Verus.
Oh no, but I didn't mean wrapper type, but I meant like permission opt. Permission opt would have an annotation saying this stuff of this type is always tracked, period. then I wouldn't have to state like I could remove like 20 tracked in this code here, if that is something I could say.
So the problem is that we cannot tell that when we're running the macro, like that we need to have run.
Yeah, you would need to hook into name resolution. Yeah,
exactly. And we cannot do this, and we are prioritizing being able to move over on the unmodified Rust compiler. So this is a compromise. And in fact, I think Chris is in the room, and maybe he can share his opinions about this as well. There's been some back and forth on exactly what syntax we're going to land on, and this might not be quite final syntax for this either.
Yeah, it's a bit unsatisfying, but I can see where you're coming from. Thanks.
Yeah, so there's in fact we have recently had a paper accepted on Verus at Uppsala, and that paper has older syntax that had the changes to the compiler that I was mentioning. The syntax there was more consistent and more satisfying, but unfortunately impossible, at least right now, to implement on modified Rust, which is a priority at this point. I don't know if Chris, you want to say anything else about this, or if I covered anything. Yep.
I think that's right. Like, this is definitely a compromise. We're not 100% satisfied with it. There are situations where we don't just have a single permission, but maybe we have a tuple of 3 permissions in it. And so that needs to be racked in a tract. So it's something where we had to be general, but we didn't really have direct type system support for it.
Thank you. And Ranjit, I think you have another question.
I apologize for this question because you may have answered it already and I just somehow missed it. But let's pretend for a moment I'm Rooston, Lino. And my question then would be, I mean, and this is an awkward question to ask at the Rust formal method. Like, what do you gain by switching over to Rust that you didn't have in linear Daphne? Because you already did a bunch of this nice work with linear. So are you getting sort of a better linear type system? And of course, I mean, the entire Rust ecosystem and all of that, but just from a purely kind of language kind of point of view, is it essentially a more expressive linear type system, or,
yes,
or is it something else?
It is. So linear Daphne was cool in the sense that it let us write a large system in it, but it didn't have the expressivity of the borrow or what you have in using the Rust borrow checker.
Right.
And so yes, we get a much more expressive type system that lets us express. And this is useful for us for 2 reasons. One is the memory reasoning, but also all of these other proof techniques that can get more advanced the more we understand, more Verus can understand what the borrow checker can do. So there's still limitations on what you can do with references in Verus. But the more we have this extremely powerful tool, and we can leverage it. And then yes, so the other part of what you said is also true, which is a lot of systems programmers are in Rust, and we want to write system software. It's good to meet them where they are.
Right.
And there's some other reasons, but I'm happy. Like if you wanna, like if you're curious, feel free to like shoot me an email and we can.
If I might, just it's not so much a follow up as it's a tertiary. Is that you kept referring to doing separation logic style proofs, but you literally mean style in that you have sort of framing conditions and you're using the type system to kind of do this, give you this kind of implicit framing. Sorry, wrong choice of words, but you know what I mean. Specifically, you don't have stars and magic ones in the specifications, right? So you're not doing any explicit separation logic, if you wish. It's more like.
Yeah, that's a very good point, and I think it's kind of one of our motivations too. Is as I may have made clear through this talk, I am originally a systems guy turned somewhat recently into a verification person, and I and other people that have kind of encountered these tools have found these paradigm easier to pick up in many ways. It's when you're reasoning about kind of concurrent code, is still complex, but we have found some of these paradigms, the way we're encoding some of these things appear to be more natural to the way systems programmers already think about the program state, how the program state is constructed. And so, yes, so that is an important distinction. And I also want to clarify that what I mean is we're writing proofs by relying on the substructural nature of the linear types. So in that sense, it's similar to separation logic. And it is a separation logic, just a different one. Cool. All right. So in the interest,
I would argue that you're basically working in a fragment of separation logic that has very nice, like easy to use syntax and a very efficient solver, which is called the Rust type checker.
Yeah, I think that's entirely accurate.
Well, I mean, sure, but by that logic, I would call the pure fragment of ML also a fragment of separation logic. So
sure, but that has none of the interesting parts of separation logic, right? This Rust has.
I know, but I really mean
has
don't have stars in
many
the
of the interesting parts of separation logic.
I just mean there's no star in the spec.
But there is. When you have two mutable references in an argument, there is a star between these two mutable references. You don't write it. You write it as a comma.
That's what I mean. The programmer doesn't write it. That's very specifically what I mean.
Sure, but that's a very nice syntactic encoding.
Oh, I agree. I agree.
Doesn't take away from the semantics.
I entirely agree. Yes.
Okay.
That's precisely what I meant.
Yep. Yeah. So let me wrap up, and then I'm happy to take more questions if there are any. So Verus is and has been open source for a while. It doesn't yet support all of Rust, as we've seen. The tutorials and guide are in progress and linked from the README on Verus, on the GitHub Verus page. We have some larger projects to kind of stress test it in progress, or this is actually line is from a few months ago. The page table is in part complete, and we were kind of successful in building a kind of single-threaded verified page table using Verus, which is cool. But we are still learning about the tool. The more systems we build with the tool. And as I mentioned, it's currently a fork of Rusty, but we're porting it to regular Rusty, and we're almost there. There's been a lot of work by Chris on this, and as I mentioned, we have this initiative that unfortunately was on ice for a while as I graduated, as I wrote my thesis, I suppose, to add Go support, hopefully, to the Rust language, because that would make some of the things we're doing easier and less terrifying to Rust developers. And actually, I have to thank Xavier on this, because Xavier has written a prototype of this, which is very inspirational, and we should definitely talk more about it. Yeah, the last thing is, you've seen this pervasive crate being mentioned a lot. That's changing soon. And there's support for multiple crates is coming, and so right now, essentially everything in your everything that's verified or has specification has to live in the same crate, including part of the standard library. You don't really want to know how that works. But we're working on fixing that, and we're moving from this kind of pervasive general library to something that's more akin to what Rust does with core and ST. Yeah, and if you have any, if you want to get in touch, please do. If you try out the tool and it breaks, please open an issue or get in touch. And if you're interested in in specific things I talked about, I can answer to some of those in depth myself, or I can point you to the member of the team, or the members of the team that have been working on that feature, and we are absolutely happy to talk to you. And we did not start in January last year. We started, if I recall correctly, in around May of 2021. If memory serves, maybe April. But yeah, it's been good progress otherwise, and a lot of work by a lot of people. Cool. All right. So thanks a lot for sticking around, and I'm happy to take more questions if you have any.
All right. Before we go back into questions, I just wanted to thank Andrea for this great talk. I think everybody here has found it very interesting, and I'm sure that there's going to be some questions in a second. So I think we can just take a moment to thank Andrea for this talk.
And thank you folks for coming, and thanks Xavier for organizing the course.
And so now we can go back to the questions.
Or maybe I fielded all of them during a talk, and we're done. Anybody else? Did I not get to somebody?
Because if you had, so I actually had a question. It was back with that example that I think Ralph was also wondering about.
Yep. Let me get back to it. I think we were talking about maybe. No, we were talking about. Sorry,
it was the one. Yeah, it was the one with the accounts, and you were taking two mutable borrows to an account and doing transfers between them.
Yep.
Right. So what? I guess what happens here in the post condition if you were to drop dest and origin way before the end of your function, right? Like if at that point, in the post state, these are uninitialized values, right?
Well, but you're not going to be able to in safe Rust, right? Like you're going to have to have. Okay.
I mean, I can drop the variable orig or dest. I'm not dropping the thing pointed by. I'm not dropping the account. I'm dropping the mutable borrow. But then in the post state itself, like the borrow is gone, right?
Yep. Well, you're going to have to put something back, right? Like I think in the signature, if you drop the binding, that will not be a valid program even in regular Rust, or maybe I'm misunderstanding what you meant.
No,
so
I mean, you can forget, or like if you at the beginning of, or somewhere in your function arbitrarily did like let underscore equals orig, and then your function can keep going on. That's totally valid.
Sure.
I think Ralph just gave another example.
Yes, good point. So the reason why we get away with that right now is that borrows that are not at the function boundary are not supported. But you are absolutely right that if we naively supported
that makes a difference. Yes.
You're totally right that if we did, and that's actually on the near-term plan for us. So thanks for the reminder. If what you're writing would make no sense.
Yes, that's the example I meant earlier. Yes, variables that are in scope as function arguments have to be live throughout the entire function. That's already a thing in Rust, modular, some mate-angle terribleness. But so then this problem can't arise. The lifetimes are always there. But if you're considering local borrows created inside the function,
absolutely,
then you can't just turn off the borrow checker because things just stop having meaning.
Indeed. Yeah, well spotted, and it's something that we're gonna take a look soon. And this is a good reminder to be careful about that.
Okay, cool. Because I mean, I saw these proposals for like Ghost code, and they keep talking about disabling the borrow check, and I keep wondering, but how does this make any sense? Okay, right. So the reality as usually is one wants, then that makes me happy. Thanks.
Yeah. Yeah. I think as somebody who would also like Ghost code in some notion of Ghost code and Rust, I think the reality is much more nuanced than just cut off the borrow checker completely.
Yeah, and I think it's the way we talked about it last year at Raspberry Pi. I think the intent is very much that the burden of soundness will be shared by, in fact, mostly on the tool. Like the tool will have to check your use of Ghost to make sure that what you're doing makes sense, given these constraints we're talking about. And it's not just, okay, you get to do whatever, and the tool is going to have to accept it semantically. The tool will have to assign semantics and potentially do more checks if it needs to for preventing cases like this. Yeah.
But to me, this sounds like you actually still want the full borrow checker. Like you don't want copy checking, but I view that as kind of separate from borrow checking anyway. But all of the parts about lifetimes, I don't see any like how you could relax any of those. Maybe there are more interesting examples that comes up. I don't know.
You may be right. So I'll be honest, I haven't looked into the more interesting example of these yet. So you may be seeing things already that I haven't yet seen, and I'd be interested to talk about it more. So yeah, once we get around to this, it might be great to pick your brain about it. but thanks for the note. And I think you're right that we need to be careful when we design the ghost feature function to make sure that we're taking into account lifetime. So that's a good point.